Hey everyone, Mr. Fransky here. Today we're going to be talking about the factor theorem, which is really just a special case of the remainder theorem. But this is really the backbone of this stuff. It's what relates this division stuff to the graphing that we were doing before, looking at like the factored form of an equation and why we can graph it, and just kind of looking at if we're given a couple of pieces of information, how we can figure out the rest of the graph. So today students will be able to relate factors to a graph and equation of a polynomial. Wonderful. So key vocabulary today: factor, x-intercept, root, zero, quotient, remainder. Stuff we've been talking about a lot but haven't really put together yet. So let's jump in and see what's going on.
All right, so let's take a look at the factor theorem. We're going to start with a warm-up problem. And the first thing we want to do is find the zeros of this polynomial. Now, I used f of x here because we've been talking about p of x a lot. And p of x is what they often use for polynomials just because p starts polynomial. But we can use any letter here we want. Remember, function notation, it doesn't really matter. So I just chose f of x this time. So we're given a polynomial here. If we were to expand this out, it would take a really long time. We could use back distribution, or we could use a lot of boxes. But all I want to do here is find the zeros. So we're actually given a nice form here. So remember, this was actually on your last quiz, to be able to find zeros when we're in a form like this. So when we have things in factors here, remember each one of these things is called a factor because they all multiply together to make this polynomial. So if we want to find the zeros of this polynomial and we're multiplying all these factors together, remember the zeros are just when the polynomial is equal to 0. So what I want to do is find out how I can multiply all these things together to get 0. Well, there's a property you guys learned in advanced algebra called the zero product property that says when I multiply all these things together and they equal 0, the only way that can happen is if one of the things I'm multiplying together is equal to 0. So my options here are x equals 0. Well, that's one solution right away, because that's my first factor. So if x is 0, then certainly when I multiply that by these other three things, I'll get 0. Or x plus 3 could be 0. Well, if x plus 3 is 0, I can just subtract 3 from both sides, and that means x is negative 3. So that's my second solution. The next one is that 2x minus 1 could be 0. And after you do this for a while, you can kind of just start to see these zeros pop out. But let's say solve this one too. So we'll add 1 to both sides. That goes away, so I have 2x equals 1. Divide both sides by 2. And then I have x equals 1/2. So that's my third solution. And my last one, you can kind of see what's happening here. If this last factor is 0, then 5x plus 2 would have to be 0. So if you subtract 2 from both sides, then we have 5x equals negative 2. And then we just divide by 5 on both sides, and we end up with x equals negative 2/5. So we have the 4 zeros of the polynomial. The 4 zeros of the polynomial. We found that by just setting each factor equal to 0 and then solving. Now, if you just look at this factor and say, well, x is going to have to be positive 1/2, because then the 2's will cancel and we subtract the 1, that's okay too. But solving out like this will work every time. So now what factor theorem is all about is, can we go backwards? So if I tell you the zeros of a polynomial are negative 2/5, 1/2, negative 3, and 0, could we get to this equation? Well, let's take a look and see if we can do that. So going backwards would mean, so I tell you that the zeros of a polynomial, I don't know, let's say that they're 1, negative 2, and 4. So the question is, could I say that that polynomial is equal to x minus 1 times x plus 2 times x minus 4? Is that true? Could I do that? And the answer is, in a sense, yes. There might be more than one solution, but these are for sure going to be factors of that polynomial. This is something called the factor theorem. So the factor theorem says that if we have a factor, so if x minus c is a factor of a polynomial, that's true if and only if the function value is 0. That means c is a 0. C is a 0 of p of x. So if c is a 0 of p of x, then x minus c is going to be a factor. Now, the way you prove this, one way is very easy. If x minus c is a factor of p of x, that means p of x is going to be equal to x minus c times some other polynomial. It doesn't matter what it is. It could be a bunch of other factors. It could be a really long, drawn-out polynomial. It doesn't matter. But if it's a factor, that means that it has to be multiplied by something else to equal the polynomial. And then if we plug in p of c, well, then it's just going to be c minus c times q of c, whatever that is. C minus c is 0. So 0 times this q of c is going to give us 0. So p of c has to be 0. So going forwards is easy. Going backwards is actually proved with the remainder theorem. So if p of c is equal to 0, remainder theorem tells us that then if we do p of x divided by x minus c, that the remainder, excuse my handwriting, the remainder is 0. So the remainder is 0 if we divide by x minus c. That means that p of x divided by x minus c has got to be equal to some polynomial with a remainder of 0. So we can add plus 0 on there, but we don't even have to do that because the remainder is 0. Multiply both sides by x minus c, and we get p of x equals q of x times x minus c, which is exactly what we talked about with x minus c being a factor. So we can go either way. Now, how is this useful? Well, the way this is really useful is exactly what we talked about on the last slide. If I tell you that x equals a, x equals b, and x equals c are zeros, if I tell you those are zeros, then x minus a times x minus b and x minus c must all be factors of p of x. These are factors of p of x. Now, there could be more. If I only give you 3 zeros and I don't tell you the degree or anything of the polynomial, there could be a bunch more factors, but we know for sure that those are going to be factors of the polynomial. So let's try an example using the factor theorem, and let me get my ink back here. So in this case, we're given a polynomial p of x, x to the fourth minus 6x cubed minus 4x squared plus 24, and we're going to factor it. So to factor it, remember, that means we're going to like put it into parentheses like this. We want to get our factors of this polynomial. And I put 4 in here because we have a 4th degree polynomial. So we're going to have 4 x's, and when they were all multiplied together, they would give us some kind of x to the 4th. So what factor theorem tells us is that we need to know what the zeros are. We need to know what the zeros are, and then we'll just be able to subtract them off here in the factors. So how do we find the zeros? Well, we had some other names for the zeros. One was the roots. Another was the x-intercepts. X-intercepts. So if we can get the x-intercepts of this polynomial, if it were graphed, then we'll know the zeros. So we're going to go over to our calculator here, and let's go ahead and add a graph. So we're going to graph this polynomial is what we're going to do. So I'm going to grab a graph, and I'm going to graph it. So I'm going to do x to the fourth minus 6x cubed, then it's minus 4x squared, and then plus 24x, So I'm going to graph it, and we're going to see it's pretty skinny. But it looks like if I went from -1 to maybe -3 up to +1, 2, 3, 4, 5, 6, 7, maybe from -3 to 7, I'll be able to get a pretty good picture. So let's change our window from -3 to 7. If you have a calculator, you can follow along with me, or you can grab one out of the case. And so now the maxes and the minima are not really important. I can get a better picture if I used zoom fit, but really what I'm concerned about, remember, are those x-intercepts. So if I can find what the x-intercepts are, then we'll be able to find the zeros, and that's going to give me my factors. So let's see what the x-intercepts are. Well, it looks like that first x-intercept happens right at 2. That one happens at 0. I don't know about these two, but there's a tool we can use for that. So if I go to Menu, I go to Analyze Graph, and I ask to find, hey, look, it has one for a 0. So the first thing it asks me for is a lower bound. So what I have to do for that is go to the left side of my first 0 here and hit Enter. And then when I go to the right, it's going to find that 0 right there. See, it says it's at -2, 0. So I can run this over, and it should be able to find all of my zeros. So my first 0 is at -2. Let's write that down. So -2 is a 0. That's x equals -2. And then if I keep scrolling over here, it looks like 0, 0, 0, 0 right there is also a 0. So 0 is a 0, x equals 0. If I keep scrolling over here, oh, it's not going to find the other ones for me. I'm going to have to find them on my own. So let's finish that. Let's go back to Menu and to Analyze Graph. Find a 0. This time for my lower bound, I'll start it here and run over to the right there. Oh, I found a 0 right there. It's 2, 0. So +2 is also a 0 for me. X equals 2. And then that last one, let's see if it's going to give it to me. Yeah, it does. So it tells me that 6 is also a 0. I can see right there that 6 is also a 0. So I was able to get all of my zeros, x equals 6. So what factor theorem tells me is that because I have my zeros here, I can just subtract them. So remember, if c is a 0, then x minus c is a factor because c minus c is going to give me the 0 there. So I'm going to subtract these all from x. So my first factor will be x minus negative 2. X minus negative 2. So let's say that's going to be x plus 2. The next one's going to be x minus 0. You can probably figure out we can simplify that a little bit. And then we'll have x minus 2 and x minus 6. So that x minus 0, that's just x. So I'm going to put that out front. So x times x plus 2 times x minus 2 times x minus 6. And that's all there is to it. We have factored our polynomial. 1, 2, 3, 4 x's. And if you multiplied this out using a box or using any method you want, repeated distribution maybe, you will actually find that it is equal to this polynomial, which is kind of cool. So just by knowing the zeros, I was able to write out the 4 factors of the polynomial. So some of you might be thinking, okay, but we can't always use a graph. Didn't we just cheat to find the zeros? Well, not really, because there are a lot of ways that we can find the zeros of a polynomial. One is graphing, like we just did. There are formulas, like the quadratic formula, which finds the zeros of a quadratic polynomial. But the point is we just have to have some way to find those zeros. And all of these statements right here are equivalent. So the x-intercept way is the way that we just used. So if c is an x-intercept of the graph of the polynomial y equals p of x, then that means x minus c is a factor. So we used 1 and 3 in that last example. And we also know that that means that the function value there is going to be 0. If we go back here and take a look, we know that when we plug any of these values in for the factors, it's going to give us a 0, like 6. If we plug in 6 for x, well, this last factor will be 6 minus 6, which is 0. And then when we multiply it by everything else, it's just going to give us 0 for the polynomial. So we know that that's true. And then c is a 0 of p of x is just a different notation, or it's just a different language for writing that c is an x-intercept of the graph. And we also know that the remainder when p of x is divided by x minus c is 0. That comes from remainder theorem. That tells us that when p of x is divided by x minus c, it's just going to equal a polynomial. There's going to be no remainder over here. Because if we multiplied both sides by x minus c, we'd have p of x equals x minus c times q of x. Shows that it's a factor. It's a factor because it's multiplied by something else to equal the polynomial. So that means the remainder, when we do that division, has to be 0 because there's nothing left. So take a minute to write these down. If you need to pause the video, you can do that. But these are important things. These are all equivalent statements. So if a polynomial with p of x with real coefficients and any real number c, following of these are all equivalent statements. So x minus c is a factor, p of c is 0, c is an x-intercept of the graph, c is a 0. Those are just the same thing with different wording. And then the remainder, when p of x is divided by x minus c is 0. That comes from remainder theorem.
And that's all I've got for you today. That's factor theorem. So not really too tough, just kind of adding a few more pieces. Next up, we got rational root theorem coming, and that's where it kind of gets fun. But the next video is going to be putting all this stuff together and really trying some examples that focus on these skills we've been learning. So please do watch the next video, and I'll see you there. Love you guys. That's why I'm here. Have a great day.